All right, so I will be talking about primordial black holes in multifield inflation, and I won't be saying anything about the actual black holes. So I will not be talking about the collapse mechanism or constraints on the mass of primordial black holes, but I will focus on how the primordial curvature fluctuations can get greatly enhanced during inflation, so that when later they re-enter the horizon during some radiation era, then they can really collapse into a black hole. Yeah, so this is what I mean by seeding primordial black holes. So a few days after we released this paper in the archive, another one appeared by the group at the IAP in Paris, and they're discussing a very similar situation, and that's very nice because independently we confirm each other's results, if you want. So this is the outline of the talk. I will start with some motivation around the discussion, of primordial black holes, and also mention how we do perturbations in two-field inflation. And then I will go to the main subject, which is how you create the black hole seeds. Yeah, how you get the curvature to get very enhanced at some desired short scale compared to the CMB. Yeah. So this is why we are talking about primordial black holes. So as we all know, in 2016, LIGO observed the first black hole merger, and later many more followed. And it seems that the mass distribution and the spin distribution of the observed black holes, they are compatible with primordial origin. So if this turns out to be the case, then you can go and ask this question down here. And because, primordial black holes are known since the 70s that are a very good, cold dark matter candidate. But you can go even further, and if you accept that these primordial black holes are formed due to some inflationary dynamics, you can use the distribution of the mass and maybe also the spins to guess something about inflation. Yeah, and this is where I want to go with this talk. Yeah, how we can obtain information for inflation from the observations of primordial black holes, if this turns out to be the case. Yeah. Right, so we already know a place where we can observe primordial fluctuations, and this is nowhere else than the CMB itself. So if you look at the CMB, you can measure the amplitude, the typical RMS amplitude of some fluctuations during inflation, and you find that it is 10 to the minus 5 or 10 to the minus 4. This you observe by measuring the variance of primordial fluctuations at CMB scales, which is 10 to the minus 9. This is what Planck says, and many others before, of course. And their statistics is Gaussian. Yeah. So now you can ask the question: what is the threshold value of the amplitude of Zeta, of the curvature perturbation, such that when it re-enters the horizon after inflation, it collapses into black hole? Yeah, and you can find this by numerical simulations. And the answer, if the black hole forms during a radiation era, is 1/10. Yeah, as you can see. So now the question that you can ask is, given a Gaussian distribution with a variance 10 to the minus 9, if this distribution is scale invariant, so if this variance is the same at CMB scales and at PBH scales, which are much shorter, what is the probability to have an amplitude of 1/10? And the answer to that is absolutely 0. Yeah, so this is a 10 to the 3 sigma event that you're talking about. So there is absolutely 0 probability of getting a value 1/10 out of a distribution with a variance 10 to the minus 9. Yeah. So the only way to achieve something like that is to forget about scale invariance or forget about the Gaussian. But let's stick to Gaussian dynamics and only consider breaking scale invariance. And how? Why is that the case? And you can easily see it here. So this is a sketch of the probability distribution function of primordial curvature fluctuation zeta as a function of time. And I use the e-fold variable as a time variable. So the e-fold n is a function of the scale k, and it is defined as the time at which the scale k exits the horizon. Yeah. So here is the timeline. You start at the time where CMB modes exit the horizon. Later, shorter scales exit the horizon. This is NPBH, and then inflation ends. You can measure your Gaussian at NCMB. You find the variance 10 to the minus 9. That sets a typical amplitude of 10 to the minus 4 or 10 to the minus 5. And what I will be discussing about is a mechanism to get an enhancement of this variance at some scale NPBH. Yeah, an enhancement of the variance by order 10 to the 7 or 10 to the 6, 10 to the 7. Yeah. So this is what I mean by breaking scale invariance. You see that at some scales, the variance or the power spectrum, if you want, gets a very big enhancement. So if you consider this case, you see that here large amplitude fluctuations are improbable, but here they are quite probable. So this is a way to get primordial black holes, the seeds of primordial black holes. Yeah. All right, so let's get some insight into the computation. And in order to do that, let's consider single field inflation. Yeah. You write down the power spectrum in single field inflation, and you find this form. So if you want a big enhancement of the power spectrum at some certain scales, you have two parameters to play with. One is epsilon, which controls the Hubble flow. That's just h dot over h squared. And the other is the speed of sound, which sets the speed at which propagations, zeta fluctuations propagate, yeah? Which can be in general less than 1, which is the speed of light, let's say. So there are known ways of how to play around with these two parameters in order to get a big enhancement of the power spectrum. In order to get an insight into the multifield case, let us focus on CS and try to understand how it appears in the single field theory. So one way to do that is to consider a two-field model with a mass hierarchy. Yeah? So imagine you have two fields. One of them is light and the other one is heavy compared to the Hubble scale. So now you can integrate out the heavy guy, and what you're left with is a single field model, but with the speed of sound which is less than 1. Yeah, it's the function of the heavy mass. So is the way is a manifestation of the fact that at high energies you have another degree of freedom that you neglect at low energies. Yeah. All right, so having this picture, let us now ask the question of what happens when there is no hierarchy. Yeah? And when there is no hierarchy, you cannot integrate out the one of the two fields. So you have a two-field model, two light fields, and when you compute the power spectrum, you will find that it is something like that. Yeah, so you have the standard ds power spectrum, h squared over epsilon, as here. But now you have a generic function of some coupling lambda of the parent theory. Yeah. So in order to connect to this picture, when you insert the hierarchy back and you integrate out the heavy mode, this f of lambda results into 1 over cs. Yeah. But in the general case, this is the power spectrum you have. So this is what I will be talking about. I will be talking about a way to compute this f of lambda in a two-field model such that, and under which conditions this contains, at some certain scale, a big bump. Yeah. So this translates to a big bump in the power spectrum. So this is the perturbation setup that we will adopt. So we have an Einstein-Hilbert term, of course, and on top of that, we add a sigma model. So this is a field space metric, and we focus on two fields, so A runs between 1 and 2, and you can do perturbation theory around this Lagrangian. The way to do it is to define a background solution. So this is the inflating trajectory. Here it is just this blue line, let's say. And on top of that, you can consider tangent perturbations, so along the trajectory, and normal perturbations, so transverse to the trajectory. Yeah. You have to also perturb the metric as a curvature fluctuation, and now you have 3 degrees of freedom. You can kill one by a gauge choice, so you're left with 2 c times psi, And you can just insert this into this Lagrangian and get a Lagrangian for zeta and psi. And you can easily see that this Lagrangian will contain a coupling between zeta and psi when there is a turn in field space. Yeah, it's easy to guess that because when there is a turn like that, as the field comes down the valley, when it enters the turn, it will just climb up a bit the wall and then climb back down and exit. And you can think of that simply as some centrifugal force. Yeah. So when the field climbs up the wall, it means that the transfer perturbation gets excited, and this can only be modeled by a coupling between zeta and psi. And if you insert this perturbation into this Lagrangian, you indeed get a Lagrangian quadratic order which contains the coupling between zeta dot and psi. Yeah, it's hidden inside this covariant derivative. And the coupling is proportional to the angular velocity in Hubble units. Yeah, so this delta theta is just the angle swept by the turn here, this angle. Yeah. So this is the Lagrangian you get. So this is a simplification. This isocurvature potential is the potential that is reminiscent of this potential here for the background. And as a choice, as a simplification, I choose to set it to 0. So now you can take this Lagrangian and you can solve the theory. Yeah. And if you do that, let me just, I mean, you can compute the power spectrum. So let me just flash the result because we learned something very important from this simple expression. Yeah. So if you solve the theory and compute the power spectrum, you find that at some short scale relevant for black holes, it is enhanced with respect to its value at large scales, at CMB scales, by a factor given by this number here. Remember, delta theta is the total angle swept by the turn. And if this factor is 10 to the 7, which is what you want for primordial black hole formation, this delta theta has to be order 4 pi. And now you immediately run into a big problem because if you imagine that you turn for more than 2 pi, you self-intersect your trajectory, right? Which is unacceptable. So there is an easy way out of this, and the way out is to consider that this metric in field space is not Euclidean, right? Actually, it has to be a hyperbolic metric, because if you are on a hyperbolic manifold, I mean field manifold, yeah, not real space, time, the circumference of a circle on a hyperbolic space is more than 2 pi, yeah? And how bigger that is depends on the curvature. But the curvature in our case is given by this coupling lambda, yeah? So if you put the field, the dynamics on a hyperbolic field space, you can turn the trajectory by more than 2 pi. You can turn by 4 pi and do not self-intersect, yeah? So this is the picture that we have. So this is the trajectory viewed from the top. So this is the moments where CMB where CMB scales exit the horizon. This is the end of inflation, and somewhere in the middle there is a turn of length of total angle 4 pi, and of angular velocity much bigger than 1. Yeah, in order to have enough curvature, so in order to achieve this without self-intersecting the trajectory. All right, so let's consider the perturbation around this trajectory. You can just write down the Lagrangian I wrote before, and you can go to the equations of motion for the fully now two-field systems, for the fully coupled two-field system. And you can just solve them numerically, but you can do better than that. You can really solve them analytically. In order to do that, you have to make a choice for this coupling function as a function of time. So this is the easiest thing you can do. You can consider it as a top hat function. Of course, that's not very realistic, but it gives you a handle into the analytics, and you see that even if you relax this condition, the qualitative features of what I will show you remain the same. Yeah. So the way to do it with this choice is a piecewise construction where you solve the theory before the turn, during the turn, and after the turn, and you just match the fields and their derivatives at the boundaries T1 and T2. Yeah. So if you do that, you can really solve. You find the solution. This is a solution for the quantum field zeta, and you can see that it contains both zeta and psi quanta. exactly because of the zeta dot time mixing. Yeah. So the interesting bit here is that it contains this frequency, these frequencies omega plus and minus, and this omega minus, it contains an unstable branch. Yeah. So this, for certain case, it becomes imaginary, and when it becomes imaginary, these trigonometric functions blow up. And this is what gives you the bump that you wanted at certain scale, k0 lambda 0, which sets the position of the term. So if you plot this solution now, you can plot the analytics on top of the numerics, and there is a perfect match. So you get exactly what you expect. Yeah. So at very large scales, which are the CMB scales, large compared to the position of the turn, yeah, you get an enhancement, but it's not very big. It's quadratic in delta theta. So for the scales that exit the horizon during the turn, which is set by K0, these are the black hole related scales. And there you have a big enhancement of the power spectrum, which is exponential in the angle. And then for much shorter scales than the scale of the turn, you don't feel anything. Yeah, so there it's like you don't have anything. It's just a single field description. Yeah, so you get h squared over epsilon. And this is exactly what you see here. So these are the large scales that get some small enhancement compared to the standard case here. And for the scales that exit during the turn, you get an exponential enhancement, yeah, that reaches the 10 to the 7 threshold that you need. So what's very nice about this plot here is that if you measure the growth of this power spectrum as a function of the scale k, you'll find that this goes like k to the fifth. And that's great because this evades known theorems about single field inflation that say that the maximal growth rate of this is k to the 4. Yeah. So this, if you want, offers a smoking gun, if you want, signature of multifield inflation on the primordial black hole mass spectrum. Yeah. So from this power spectrum, you can compute the mass spectrum, and this slope turns into a statement about the mass spectrum. So if in the future you manage to, if what we see with LIGO are primordial black holes, we can measure the mass function and look for this slope. If it is k to the 5, then you can say it's multifield. If it's k to the 4, it's single field. Yeah. And the other nice thing about it is the fact that exactly due to the fact that the dynamics of the enhancement are completely independent from the Hubble flow dynamics, in this picture here, in this mechanism, you don't break slow roll. Actually, you don't disturb slow roll at any point during the evolution of the perturbations. Yeah? So this is more or less what I want to say. We have presented a purely multi-field mechanism to get an enhancement of the power spectrum, which provides a seed for primordial black hole formation. So we saw that there is a need for a non-trivial geometry. You have to put the theory on a hyperbolic field space in order for this to work. We saw that the dynamics of the enhancement of the power spectrum at certain scales is completely decoupled from slow roll dynamics, and due to this fact, you evade known theorems about the steepest growth in single field inflation. And finally, I mean, this strongly coupled, strongly mixed theory, which goes under the name rapid turn regime, has been studied in the last 10 years, more or less. There are many papers on the subject, and at least to our knowledge, we were the first to give some analytic solution of the full dynamics for a time-dependent function. So this is more or less what I wanted to say. So there are many things to do, like inserting non-Gaussianity or talking about the gravitational wave spectrum that comes out of this enhancement of the scalar power spectrum. We can discuss if you want in the discussion session, which I hope to see you there. So that was it, and thank you very much, and bye.